Hello, my name is Haneul Kim from IIIXL Lab. The paper I'll be presenting today is titled Collaborative Research for Enhancing Embodied Multi-Agent Collaboration, published at CVPR 2025. This work explores how we can make multiple embodied agents plan together more effectively by combining the reasoning power of LLMs with the structured search capabilities of Monte Carlo research. In other words, it tackles a key question. How can agents communicate, adapt, and cooperate better in complex environments? Let's first take a look at previous methods. Koala, presented at ICER 2024, is a framework for embodied multi-agent collaboration based on LLMs. It consists of 5 modules and allows agents to independently create plans and communicate using natural language based on their individual memory. However, it lacks mechanism for establishing shared strategies and supporting flexible replanning. Then came Capo, presented at ICER 2025, which improves openness by first generating a meta plan before execution, and then incrementally adjusting it as a situation evolves. However, Capo has also its drawbacks. It relies heavily on the initial meta plan and struggles to adapt flexibly during execution. Moreover, since Capo follows a single-pass reasoning approach, it cannot recover from critical errors. To overcome these limitations, COTS, proposed as CVPR 2025, introduced a collaborative research strategy. Agents can generate various planning paths and collaboratively evaluate and select the optimal one. Thanks to LLM-based reward evolution, backtracking is supported and a wider range of possibilities can be explored. Okay, let's dive into the framework. COTS consists of 4 key modules. First, perception module. This module is similar to Koala's, but includes distance information, enabling agents to better perceive objects, states, obstacles, and the positions of other agents. This addition is crucial for strategies like search the nearest loom first. Memory module stores agents' observation and actions. While prior work used only short-term and long-term memory, COTS introduced an intermediate form called extended memory. This is important because collaborative plans aren't completed within a few seconds. They must be retained for a while, but still allow for updates when necessary. This is the core of COTS, where agents generate and evaluate multiple plans to find the best collaboration strategy. Let's talk about the key method here, Monte Carlo research, or MCTS. MCTS is a strategy often used in games like Go or chess, where various options are explored in a tree structure using random simulation to find the best path. Think of each node as a plan and its children as slight variation or extensions of that plan. COTS adapts this idea for multi-agent collaboration. Rather than following a single plan, agents generate and explore multiple alternatives, selecting the best strategy collaboratively. Alice, acting as the planner, proposes a step-by-step plan based on current environment. For example, step 1, Alice grabs apples, Bob explores his current loom. Step 2, Alice explores the living room. If they find any items, transfer them to the bed. Then Bob, acting as the critic, evaluates the plan, giving natural language feedback and a reward a score. For example, the plan looks good, but the other place is closer, with a reward score of 0.6. This process builds a tree, not a single chain. Each node represents a joint plan and feedback, and each node can expand into multiple children representing various collaborative scenarios. Now, let's take a look at how COTS decides which nodes to expand in the tree. It uses this formula called UCT, or upper confidence bound for trees. We can break it into two parts. First, we have V of S of I. This represents the average reward of nodes S of I, meaning how good that choice has been so far based on previous simulations. Then we have the second term, W times the square root of log n of P sub I divided by n of S of I. Here, n of P sub I is the number of times the parent node has been visited, and n of S of I is the number of times the current node has been visited. What this means is, if a node hasn't been visited very often, this term becomes larger, which encourages the model to explore it more. So, this equation strikes a balance between exploitation and exploration. It favors nodes that have performed well, but still gives a chance to underexplored options. The selected node is expanded into n child nodes based on the Alice plan and Bob's feedback. While classic MCTS use simulation to compute rewards, COTS use LLM-based inference to estimate plan quality. Two key criteria are used. First, task assignments qualities, like coherence and divisions of labor. Second, efficiency in movement based on distance. Each is evaluated and normalized into a reward score between 0 and 1. Next, backpropagation. The reward from the selected node is backpropagated of the tree to influence future decision. For example, if a plan gets 0.9 rewards, this positive outcome will also strengthen the earlier nodes that leads to it. In this way, COTS avoids relying on a single response from the LLMs. Instead, it generates and evaluates multiple candidate plans, ultimately selecting the most effective one. This enhances collaboration consistency and overcomes the randomness and inefficiency of conventional LLM-based systems. This is designed to continuously evaluate whether the current plan remains valid. In COTS, agents collaborate based on a shared plan, which can be adjusted according to changes in the environment. However, COTS identifies two major problems in this context. If the plan isn't updated often enough, it may no longer reflect the current situation, leading to incorrect actions. On the other hand, if the plan changes too frequently, agents may be interrupted mid-action, causing confusion and inefficiency in the entire system. To solve this, COTS introduced the plan evaluation. As task process, the system checks whether the current plan is still valid. If so, the plan is maintained. If not, a new plan is generated. Importantly, COTS doesn't overreact to small changes. It evaluates whether the overall plan still makes sense rather than reacting to every minor fluctuation. This mechanism helps reduce unnecessary LLM costs, ensures plan consistency, and allows agents to respond appropriately to changing environments without being overly reactive. The final module is the plan parsing and execution module, which translate high-level natural language plans into actual agent actions. This process consists of 3 stages. 1. Goal plan understanding. For example, if the agent is told, Bob, bring the cupcake from the bedroom, it first interprets what the goal is. Second, action decomposition. The high-level goal is broken down into the sequence of concrete steps. For example, go to bedroom, pick up cupcake, go to bed, and place it down. Last, action execution. These steps are executed by the agents based on its current state. For example, the agents can only perform the grabs action if its hands are currently free. In this way, COTS ensures that natural language instructions are smoothly and logically translated into physical agent behavior. Before show the main results, let's see the benchmark. 2 benchmarks were used to evaluate COTS. First is CWA, Collaborative Watch and Help. This benchmark involves multi-agent collaboration in household tasks. For example, agents might be asked to put the cupcake in the sink and the apple on the table, starting from different locations and coordinating their roles through communication and task allocation. Second is TDW-MAT, 3D World Multi-Agent Task. This benchmark uses the high-fidelity physics-based 3D world simulator. The goal is to transport multiple objects. For example, 3 apples, 2 oranges, 3 loaves of bread onto a bed within a 6-room apartment. The task requires strategic collaboration, exploration, and long horizon planning, making it effectively challenging. Let's begin with the main results. As you can see in the table, COTS consistently outperform existing methods such as Koala, Rocco, CAFO, and RHP. In particular, on the TDW-MAT benchmark, within GPT-4 and Oracle Perception, COTS improves over Koala by 9.4% on average. Without the Oracle, the improvement increased to 16.9%. This clearly demonstrates the effectiveness of COTS tree-based planning strategy and the planning evaluation model. This is the qualitative analysis. Through these examples, we can see the COTS supports long-term strategic planning, effective role assignment, and plan consistency. First, picture A. When Bob is searching for 2 target objects in the living room, Alice is already holding a container. In Koala, Alice inefficiently moves toward Bob to pick up items. In contrast, COTS allows Alice to explore her own room, deliver the objects to the bed, and only then move to assist Bob, minimizing unnecessary actions. Then picture B. Alice and Bob are in the same room. In Loco, both are instructed to explore that room, causing redundant work. But in COTS, Bob explores the current room, and Alice moves to the nearest unexplored room, which reflect efficient task division based on spatial context. Then picture C. While Bob is transporting an object, Alice discovers a new one. In Loco, Bob abruptly stops his tasks to assist Alice, which interrupts task flow. In COTS, Bob completes his original task first, then transitions to the next action, preserving logical flow and avoiding chaos. This image illustrates how COTS plan evaluation work. In the next left image, both agents are empty-handed and idle. This triggers the systems to assign a low reward of 1, indicating that a plan updates is needed. In the right image, one agent is holding a cupcake and has discovered an apple in the fridge. Since the current plan aligns with ongoing action, a high reward of 4 is assigned and the plan is preserved. This example shows how COTS doesn't blindly stick to plans, but evaluate them based on progress, updating only when necessary. This allows agents to collaborate efficiently without frequent disruption. Let's now look at the ablation study. In the top left table, table 3, you can see the performance impacts of removing core modules, reverse scrolling, tree planning, and evaluation. All three are crucial to performance, and notably, removing MCTS leads to a steep drop in collaboration efficiency. In figure 6, we see the change in transportation rate over time for COELA via COTS. It's an analysis of agent collaboration progress at different time steps. COTS starts off a bit slower but overtakes COELA after 2,000 steps, highlighting its strengths in long horizon strategy. And next, figure 7 examines how the branching factor, the number of child nodes generated in the tree, affects performance. A higher branching factor allows for more exploration and better plans, but it increases computational cost. So there's a necessary trade-off between performance and efficiency. Conclusion. COTS is a collaborative framework that integrates LLMs with a modified Monte Carlo tree search. It enables agents to explore multiple planning paths and adapt strategies based on task progress. The plan evaluation modules ensures execution stability by updating plans only when necessary. And as shown in benchmark, COTS significantly outperform previous methods like COELA and LOCO on complex multi-agents embodied tasks. But it also has a limitation. COTS relies on the reasoning capabilities of LLMs, which can vary in quality. And GPT-4 performs significantly better than GPT 3.5 Turbo, especially in instruction following and answer quality. That said, even GPT 3.5 showed notable improvements when used with COTS planning tree structure. To sum up, COTS shows us a promising direction for collaborate agent planning and combining the structured search of MCTS with the flexible reasoning of LLMs. But we're still at the beginning. As we move forward, we need to ask, can we make this system less reliant on powerful LLMs like GPT-4? Can we reduce their cost and improve robustness in the real world? In the end, the goal is clear: to build agents that are not only intelligent but truly collaborative, scalable, and reliable in dynamic environments. Thank you for the listening.